Okay, so we look live. Doesn't look like we have any live viewers at the moment, but that's okay. So let me just, I have a little chat windows on my Steam Deck. Okay, hopefully I can keep up with chat a little bit better with it on my Steam Deck. And then let's just hide the chat box real quick. Okay. Oh, look at, we have someone, looks like on. Hello. Yes. Patel, let us go and talk about the Avnet ZUBoard. Okay. So today we're going to talk about a new dev board. I just got it in the mail, so it was shipped this week. So we're going to explore its different features, its nuances, whatnot. It's a Zynq UltraScale Plus MPSoC FPGA. It's fairly affordable. It's $160 at the moment, and you have a good amount of I/O and features on it. So yeah, let's dig a little bit into it. I mean, we can see the board in the top right and the other various pictures. Some obvious things. Let's talk about obviously why we have it right here. We have Ethernet, USB host. We have a micro USB to FTDI for JTAG and UART, and we have power over USB-C. I have a power monitor as well, so we can see what the voltage is and current. We also have a SD card, and then we have some dip switches, some buttons, some RGB LEDs, and looks like we have user LEDs as well. We have 4 user LEDs. Then we have the click it, and then 3 syzygy interfaces. So let's kind of go through the quick review. All right. So this is a cheap MPSoC device. So it's fairly powerful when it comes to like a SoC system. It's new, but I mean, it's still been this variant of the MPSoC is brand new. So going to the question, Patel, the pink Z2 is a Zynq FPGA, right? So that's the Zynq with a Series 7 fabric. This is the UltraScale Plus MPSoC. In this one, is it A53s or is it? I might be mistaken. It might be different processors. Let me go check real quick. Yeah, they're A53s. Okay, so that's what's on the main thing. There should be a smaller processor. The A53s in the Zynq as well? It might be, but so this is like the next generation of the Zynq 7020. So this is very equivalent to what the Zynq 7020 is, but smaller silicon, so you get better power, better performance and timing, faster processor speeds, low power. So it's going to be like a better version of what processor of the FPGA that's in the pink Z2. Okay, back to the slides. So this comes with board files, some basic board files that you can quickly set up a block diagram with the RGBs, the click it, some I2C buses. They don't really have the syzygy and syzygy example set up yet. JTAG over USB. So the I/O are kind of split into 2 sections. You have the processor I/O, which is the UART, Ethernet USB, the MOI expansions and MTG lanes that are on the transceiver syzygy ports. Then you have the PL, which use a variable speed bank or power or voltage bank, where you can go. You have a jumper over here on the right side that goes between 1.5 volt and 1.8 volt. That's for the micro E, but the micro E is scaled to 3.3, so you don't have to worry about the voltage for that. but the Syzygy IO for this connector and this connector come from the FPGA fabric. So I did some FPGA stress testing on this to see how much power and heat that it can withstand. So I was able to make a design that did 100% VRAM, 100% DSP at 250 megahertz. According to the USB-C monitor, we got up to about 9.7 watts, and according to the FPGA system monitor, we were about 96 Celsius, which is like the edge of operation, right? We can't go much better than that. But being able to run everything at 250 megahertz, 100% utilization type of stuff, that's pretty good performance without, putting a fan on it. I bumped it up to 300 megahertz, and we got up to 10.5 watts, and there was thermal runaway. We couldn't, the FPGA went beyond the spec of 100 Celsius. So after 100 Celsius, it turned it off and whatnot, but it seems to be able to utilize the FPGA pretty well in the given power, temp, and heat, thermal dissipation that it currently has. So yeah, I think those are the good points. Let's get to the bad and weird points. So this system only handles USB-C at 15 volts. So you can normally have like 3, 5, 9, 12, 15. There's different voltages you can do it at. The power connector for this must be able to do 15 volts. So this, for me, I have a Steam Deck and a Nintendo Switch. Worked great with those chargers, so I didn't really have an issue so far. But like if you use a phone charger or any other USB power source, it's not going to work. You gotta have a high quality one. And if you have a power bank, you're gonna have to get a power bank, battery power bank that does 15 volts, and only really up to 1 amp. I couldn't get past 1 amp as soon as I got to 10 watts. Below 1 amp, it just couldn't handle the thermal load on the FPGA for that. So I think a 1 amp 15 volt charger should be sufficient. Okay, so for MP-SOC boards, you usually have a video out. The processor has a hardened display port, and the display port goes out the transceivers, right? So the transceivers are the two bottom Syzygy ports. So if you want to use the display port, you're going to need to have a Syzygy to display port converter. I might look into making one of those. The output version of this should be pretty easy. Input display port would be madness because that's go through the fabric, have a soft core, everything. But an output display port on this would be pretty easy to do. So I might look at maybe designing a PCB for that. Okay, the next sad thing is the processor has 4 MTG lanes. And those MTG lanes have rev clocks. There's 4 rev clocks available in the processor. You have 1 rev clock coming from here, from this connector, 1 rev clock coming from this connector. The last 2 rev clocks are not even populated. I really wish they had an onboard oscillator that you could have a onboard a ref clock so that you could do Ibert testing and whatnot. You should have had an onboard ref clock. It's really weird you don't. Next one, we have the LPDDR4, 1 gigabyte. This is only running at 1066 gigatransfers per second. This is due to the limitations of the FPGA and the FPGA fabric. Usually with the UltraScale Plus, you can get to up to 2400 giga, at least on the fabric side. The processor side, you're probably like 2000 to 2166. So it's kind of surprising that it's so slow. It's probably the LPDDR, the low power as well. I bet if it was higher power, you could go a little bit faster. I'm going to play around with some constraints in Vivado or Vitis to see if I can overclock it at all. But currently, that's kind of the max. So Avnet, the company that's designed this board, currently has no reference designs. They do have like a MATLAB tutorial, but didn't seem that there wasn't really source code, and you need a special license to use the MATLAB Simulink Vivado model composer tool, so it's not really open for the hobbyist and the student who buys this. This board can run Petalinux. I did not find a Petalinux example so far. Usually Xilinx provides Petalinux examples for their dev boards, and Avnet also provides Petalinux examples for theirs, BSPs they call them. I haven't seen one yet. Pink could easily run on this board. I would love to see Pink on this board, but it's usually running on top of a Ubuntu-like OS. I may look in trying to build a Petalinux image, but it's not the easiest thing. Also, Vitis AI. Vitis AI may fit on this device. I'm not sure what the smallest DPU is available, but we might be able to run Vitis AI on this board as well. Okay, the ugly. So we need to talk about the Syzygy ports. The Syzygy ports are technically not compliant with the Syzygy standard protocol. That's done by Opel-Kelly. It does not support smart VIO, which is the adjustable voltage. And this is kind of similar to FMC with the bigger Xilinx dev boards. FMC connectors usually have an adjustable voltage where there's an EEPROM on the FMC module that tells you what voltage to use. Sometimes they had a system controller that would, change the voltage, but a lot of times it was a jumper. Like in this situation, there's a little jumper that changes the voltage. But so we don't have any smart adjustable voltage. It is manually controlled. There's no smart power sequencing that will prevent you from sending the wrong voltage to your board. It's always on, so there's only a manual check for compatibility before you put it on. So you must be smarter than the hardware when trying to get Syzygy boards to work. I'll try to look at compatibility. I don't have all Syzygy boards. The Syzygy boards are kind of pricey. I hope Avnet maybe releases a few affordable ones that work well with this board. I'm surprised they didn't have, a compatibility list or release some Syzygy boards along with it. I didn't see any plan for some, so it was a little bit awkward, I would say. I was expecting more Syzygy expansions on it. So this is a good IoT edge device. It's Xilinx's new low power cheap family. So hopefully it's good for edge processing, IoT. You can do video pre-processing, real-time motor controls, Vitis AI if it's big enough. Figure that out later. The cool thing with the transceivers is you can do PCIe root complex or endpoint. I'm going to use it to explore PCIe and learn how PCIe works on a low-level software FPGA level. So that's kind of my goal in using this board. Okay, the next thing is there is Vitis model composer tutorials for this board, but that does require a full Vivado license. So maybe this board would be good for a classroom or a university where the university has licenses for model composer, so you can do some good DSP work. I might explore that, but that's kind of beyond the Webpack license, so I'm not as terribly interested to explore it. As with that, it's also a good educational platform. These MPSoC, the processor of FPGA combo devices, are really useful, and it's a really hard skill to acquire, and it seems like a skill that's needed in a lot of FPGA PCB development. So you learn how FPGA works, how the processor works, how they intercommunicate, be able to read the technical reference manuals. It's a very, very, very good skill to have. Okay, so that's kind of the dry presentation. So let's go and play with designing with the board files and getting some performance readings on the various processors that are available. So what we're going to do is we're going to open a brand new project, and we're going to build it from scratch so everyone can see call it board, I guess. We're going to build it from scratch so everyone can see. We'll do a Vitis platform another time, but that would be fun to do this. So you go to boards, you click refresh. I'm not going to do that right now because streaming and refreshing this GitHub repository is a bad idea. You go to vendors, we go to Avnet, scroll all the way to the bottom. We have the ZU1 board. So we have the Syzygy connectors. but there's only the Vision AI starter card. There's no other JSD modules inserted yet, so we're not going to use it. But yeah, let's go ahead. I should look at adding my own connectors. So let's hit next and finish. We'll keep this one open. So let's build an MPSoC device in a block diagram from scratch. Okay, let's get a screen. Go ahead and get out. Close that. Close that. Everyone can see a little bit better. Good. So first thing we're going to do is we're going to add the MPSoC. So the MPSoC has a bunch of processor pins, and you need to use the board preset on this, and this is going to define the clocks, the I/O, and everything on the processor side of the IC. And let's go ahead and take a peek into how this is configured. I need to make this smaller. Vivado is a program that should be run on a 4K screen, so I'm sorry if you have trouble seeing how this works. So here is kind of a quick block. And mostly it's right over here in the MIO that's important to pay attention. I also need to learn how DMA works, but we'll get to that later. We'll also look at the DDR controller. So this is the flash. We have the Ethernet. The Ethernet is using RGMII. We'll look at that in a second. USB. That's the SD card, the SPI, and I2C. I'm not sure what those are connected to. We might want to pull up the schematic and see. But we have a SPI, and I2C, and a UART. Actually want to look at the schematic. So let's go on an adventure. Time to go look at the schematic. I am curious, and I want to know that and look at it now before I forget. So you can read the user guide, it's useful and whatnot, but I am a schematic person. The schematic is how I hunt down all the necessary stuff. So we're going to look at the bank, one of these banks, right? Okay, let's look at what pins they have it connected to. Okay, so we have, go to IO right here. We're going to expand it all. We have the QSPI here. Yeah, the SD card. Do I2C 8, 9. So we go back here, look at 8 and 9. Brought me here. What am I looking for? Okay, so let's see. It's saying go to page 7 to D. Page 7 to D. Okay, it's going to the Mac EEPROM. Okay, that probably has the Mac address. Yeah. EEPROM 7-bit device address. Okay, so this is just the Mac address. Okay. Okay, then we have the PMU. That's interesting. What the PMU is. So it's 26 and 34. I'm gonna hunt this down. Okay, so we're gonna go look at 26 power initialization and 34 power kill. Okay, that makes sense. The SPI bus is 38 to 43. 38 to 43. So we're looking at 14.1a. So let's go look at page 14.1a. Okay, so the pressure sensor. We have a pressure sensor on the MIO. We should learn how to read all these things. I'll have to look up documentation for that pressure sensor. The temperature sensor is going to the FPGA. Any other fun sensors here? Off on controller, off on sequencing. Okay, so we defined most of those sensors. okay, no, go back to this one. The UARTs, GPIO, a bunch of, I think most of this is just going to the transceiver. Let me see. So this is going 13, 30, skipping some. We have a few on the end. Page here. SD card. MIO 44, GPIO switch. Okay, switches, LEDs. Oh, okay. So the 4 LEDs are going to at least a few of those. 91A. I'm gonna look at 91A in a bit. LED 1. Okay, so it looks like we have 4 LEDs there. Anything interesting over here? RGMI, USB, and the gem. And then we have JTAG. Okay. Can't reprogram that ref clock, can I? Nope. Hard coded. Okay. So I think that's about everything on that side. So for the high speed, okay, let's minimize the low speed and talk for the high speed real quick. The Ethernet is using RGMI. We can you can do PCI, DisplayPort, and SATA, but you need a syzygy connector for that. Be interesting to have. There's PCI 1 you can get, but I don't know if DisplayPort or syzygy. It's probably okay, let's see. Okay. User G data. I do not see a syzygy SATA port. And syzygy display port. Okay, yeah. We don't have anything that can do that. I guess we'll maybe design some. I don't know. Sounds hard. Okay, so clock. They have a bunch of manual clocks here. So they enabled manual mode, which is really surprising, and they went through. And put in every multiplier and divider. I was trying to get the right here. So where's the DDR clock? DDR clock is whatever is the 533. So this is a DDR clock, right? I wanted to run it a little bit faster. So this is the DPI. So if I go to DPI and be like, hey, let's multiply that a little bit faster. And we need to find a way to lie to this and be like, hey, don't worry about it. I'm going to do things. Is there anything else that's off the DPI clock? Um, can't go like what, 3? Okay, yeah. So I don't think we can oh you want 4. Okay. Yeah, so there's not really I need to find a good way to overclock the DDR. Okay. So here's our DDR configuration. We have a custom LPDDR4. It's going to be twice this speed, so that's where you get the 1066 from. But like if we try to go what 550, right? It's going to give us 533. There's no way to be like I want 800. It's not going to change. That's the speed. Gonna have to play around with overclocking. I don't think there's anything special in here. And that's just your other stuff. Okay, so that's the processor configuration. So let's go ahead and drop some board components down. We're just going to do the LEDs because they're an easy one to do. And then we're going to drop in a microblaze. We're going to do a 128. We don't need no cache. We're going to debug in UART. If you have, we don't need UART, but we should be fine. Fun to see how delayed my streams are over here. Okay, so we're gonna run a connection automation. We're gonna do it to the microblaze, and then we're gonna add the other guys. Then we're gonna microblaze. We're going to do maximum performance, but we're gonna turn off the instruction caches. Caches are only good if you're using the DDR memory, and we are not using any DDR memory. At least in this setup. I guess we could try doing test the DDR memory, but I don't have that set up at the moment. Okay. And we're going to validate. There's something hiding over there. I can't. Quick help. Okay, good. So to get this running, we're just going to go to the top, create an HDL wrapper, and then build it. We already have it built, so we'll flop over to the design that's built, and we will do some Vitis development. Okay, so to the other one. So this one is already built. We have the block diagram. Let's go ahead. I want to open the implemented design real quick. But we have the block diagram here. All nice and situated. Let's open up the implemented design. I want to talk through this real quick. And I haven't looked at the floor plan for the this Zinc Ultrascope Plus. I'm curious to what the floor plan looks like. Didn't take long. Okay, I do have some water. Good. You unhappy about something? The output delays, that's fine. You'll be fine there. Okay, methodology. You are That's fine. The B scan. Okay, you're all fine. Let's turn this off so I can see what we got here. So so this is our processor right here, and these are our 3 clock domains. And we can go look at the different components, right? So these should be BRAMs. Yeah, so that's a BRAM. Let's make this easier to see. Oop. And add a little bit. Okay, cool. So we have BRAM there. Are they the DSP should be, are we using any DSPs? Logic. I did select a lot of VRAM. Okay, here's the DSPs. interesting how they have it highlighted. Oh, look, you can actually, can we see the configuration? Oh, I guess we could open the routing. Oh, ouch. That's not very useful. Like it's using everything. Hmm. I just want to curious that there's, okay, there's the DSPs. So here's what our FPGA looks like. Let's go ahead and export the hardware. We're going to export the hardware of the bit stream. This is just going to be an XSA file that's just going to sit in our project directory. Finish. Go clear the chat real quick. Okay. If any questions, please ask. If you're watching, mostly looks like Twitch at the moment. Okay, so we're gonna go to tools. So we're gonna say launch Vitis IDE. And let's do some processor stuff. It'll be fun. Exciting. Let's start with the small processor, right? Or let's go, we want to go R5, Microblaze, A53. Let's jump around a little bit. Okay, so what we're gonna do is we're gonna create our own little directory. It's gonna be in the test.k. Oh, it's on the window. Bring it over. Okay, so let's walk through how we do this. We're gonna go create a new platform. We're gonna browse, go to our directory. Too many FPGA projects. Okay, and we have the top XAA. Okay, first stage bootloader. I'm not really going to use the first stage bootloader, but yeah, let's do that. Sounds good. So we have the Microblaze listed here. We're going to do the R5 first. And this is going to be hello. So, well, no, we'll do a hello project, and then we'll do a dry stone project. We'll get hello world from everyone, and then we'll do a dry stone project from everyone. So this is a system project. Yeah, okay. Main. We're gonna do hello world. We'll do dry stone next, and then we'll do the. Where's the zinc memory test? Not on this one? Maybe it has to be done by the A53? That's weird. We'll look when we do the A53 one. Maybe it's only an A53 demo. But hello world it is. So what we're gonna do is in our platform right here, we're going to go to the board support package for the R5. And we're going to go modify DSP settings, standalone. There we go. There we go. We hit OK. Now we're going to go to Hello System and build that. It's going to take a bit of time because it's got to do the it has to redo the whole board support package because I mean the first time, but every time I change all those little IO outputs for it, it's going to be angry. So we're going to do Microblaze and then 853. Yeah, we got all the Hello Worlds running. I want a new console. There like a way I can have multiple windows? Yeah, let's do a new console view right here. And I can't see it at the moment. We'll see it in a second. Go ahead and grab that one. We'll stick this one in that. A little bit smaller, make it deeper. Okay. Good. So now we're gonna run this on the system. Okay, we're just gonna run it and hope it. I like to change some settings, but we'll do what we can. Okay, so here we have Cortex. So we go to R0, you can see it ran Hello World successfully. The RGBs turned off. While we're here, let's go play with the RGBs. Okay, that's blue, green, red. Okay, let's go to the soft real quick. I wanna play around with something. We want to include Xyle io.h. I think it's gonna be Xyle out. I want to do out 32. Why not? The address 1, 2, 3, 4, and the value will be yeah, 4 there. Well, this one we're gonna change. We'll change to 2. We'll change that to a 4. Okay. We see the red LED. Now we've done that. Let's rebuild it. And we're gonna go to the run configurations real quick. Target setup. I like to use the tickle script rather than the first stage bootloader. It seems to be a more reliable thing for booting up often. And then we can go into the tickle script and maybe change the clock speed. Programming the FPGA. Oh, it's 8. Oops. Okay, let's hit run. It's going to rebuild, right? Didn't like that reset earlier for some reason. Okay, we have green and red. Great. I'm happy about this. Probably that hand. Okay, so let's go ahead and add a new application. We're going to pick the same domain. We're going to go here and we're going to target the Microblaze. Okay. Hello. B. Whoop. Standalone microplays. Hello world. So now we're just gonna build the whole system. And do new console view. Put it right here. It's great. It's going to be set up on the microplace, and you're going to be set up on the 0. Okay, so we're going to go to run configurations. We're going to go to target applications. Yeah. We're going to turn on the microblaze. Do hello. Well, you could turn off the programming of the FPGA. Okay, so microblaze, hello world, and R5, hello world, and let's go get the A53 going. Okay, so now we're gonna do a whole new application project. Yeah, right here, show the processors. Then we do the A53 processor. I wonder what people think about this raw, like looking at every single step, because I feel like for a lot of people it can be annoying for, like, I guess, entertainment, but it's really good when you're like, hey, I want to get this working. I have a step-by-step video I can follow perfectly, and and I should have no problem. Um, until you have something. Okay, I want to run those DRAM tests later. Okay, we'll do this, then we'll do a whole thing of dry stones, and we'll have fun watching the different outputs. Okay. I'm gonna have to change the output for this. Okay, so we're gonna go back to the hello system real quick. We're gonna go to platform. And now we're gonna go to the A53 standalone. Let it load. We're gonna change it to the core site output. So here, up arrow, up, I know, double click. I don't know why my arrow doesn't work for that, but I can double up click. Okay, we're good. And it's gonna generate VSP. It's gonna be upset about it. Build everything, run it, then do dry stones. Okay, now we're gonna click hello system and we're gonna build it. Okay. What did you have with the problems that you have? Sheesh. Yeah, that's fine. It's only 1 gig. It's not gonna go to the DR1 hard drive space. But yeah, it's fine. Okay. There. Configurations, application, turn on A53. Hit apply. Go to target setup. We'll do RPG. RR. Ah, more. Get one to split mode. We just reset those. Oh, everything. Ish. Run. You didn't like the reset. Okay, we'll hit again. Okay, so we can now see the output from all the processors in the system. Got the Microblaze, the R5, and the A53. Okay, so now we're going to create a whole new application project, and it's going to be, we're going to do Drystone, and we're not going to run it until we get all of them. Over here, we're going to create a dry. Can I like do multiple processors? Do the A53 first, and then we'll just go through and through. Um, Standalone, yes. Drystone. Finish. Okay, that's cool. Now we're just going to go new application for the other guys. Top. We're gonna try for the R5. Oh, R5. I should have done the name on the other one. Oh, no, I can't do one at a time. Drystone. Finish. Okay. Again. E alone. Fetch those applications. Drystone. Oh, at one of those. You know what? Microblaze, we can do it another time. So it doesn't do the proper timing unless I put an AXI timer into the system. And I could, but I have to rebuild the bit file and get everything going, and I'm not doing that today. I'll post results on a post or Twitter or something. We'll figure it out later. Okay, we're just gonna do 2 dry stones. That's fine with me. We're gonna build it. Okay, what warnings did we get? I don't like when there's warnings. That's fine. I can deal with that. Okay, so we're gonna go on configuration, and we're just gonna switch out the project, right? We're just gonna say can I just right here. We're just gonna browse. Oh, that's the microplace. Okay, yeah, A53 dry. You will do dry, apply, and we'll run. Okay, are you gonna cry about the reset? You're probably gonna cry. You cried about the reset. That's fine. Let me figure out what the reset issue is. Okay, so let's go look at the R5 and we'll go look at the A53. Like it should Demus per hertz. I feel like I got better numbers before. I'll have to look at the other video. The R5's thinking. Oh, did I not do the optimizations? I might have not done the optimizations. Build settings, right? General, no. Optimizations. Yeah. Let's just do optimize most supply and close. Here, we're gonna go to stations. We're gonna do most supply. I know there's other flags. The dry stone compiler flag. Okay, there should be like Okay, let's go to GitHub soft by yes, this one. Okay, we're gonna go to master bench make file. That's the optimization flags I usually run. Yeah. Yeah. Why? Okay. Core dry stone. We're doing O3. Okay, right there. We want to do O fast mount. Right there. We want to do that. Do those two. Okay, so let's go back to these builder settings. I don't add that. Apply close. Build settings. Also, let's look at the linker scripts. Let's try to keep this as close as possible to the system. Apply and close. So we're gonna look at the linker script. Right here, we are running whereas everything is in DDR memory. That's gonna make this one slow. So what we're gonna do is we're gonna generate a linker script for this guy, and we have plenty of space in the OCM. So we're gonna put everything in the OCM because that should be faster. We'll probably do 4 each. Generate. Yes. Okay. Here, what are you doing? You are running with everything in DDR memory as well. That might not work. Okay. You are going to go into the TCM. Let's put you in the TCM. So we're gonna go put you in the TCM, and we're gonna put you in the BTCM, and you in the BTCM. The TCM is plenty big, so it's gonna make you 4 and you 4. Generate. Okay. So we got pretty poor numbers last time. Now we're going to rebuild and see if we can get better numbers. Anyone comment? Nope. Okay. Are you gonna? It's probably gonna yell at us because having trouble resetting back and forth. It seems happy enough. Okay. So let's put you on R0, put you on A0. Okay, that did much better. You, on the other hand, are not happy about something. No warnings. I'm kind of curious what that is. Maybe I can get rid of the what is it? It's assertion Bolic succeed. Yeah, interesting. Let's see what happens. Okay, we have this really interesting. Okay, so let's try. That's really good, but let's try turning off we're gonna do the A53 by itself and see what happens. You might have to change the linker script. OCM RAM should be plenty of space. I have to do the DDR. Okay, it didn't like that. Generate linker script. Guess we could put those in the DDR. See if that changes anything. Generate. Build. And we're done. So run. Where'd that bolic exertion come from? Weird corruption of the system? I don't know. Okay. Let's go to this then and apply and close. Generate linker script. Let's go back to the OCM RAM. Should be faster. Plenty of space. Okay. Looks like YouTube has a better latency than Twitch does. Which you look like a few minutes behind. Wow. Okay, the reset. Play. It's still angry about that. Maybe it's something to do with the optimization. Let's go to build settings. We'll do optimize none. Okay. Run. Oh, you want me to build? Run. Okay. Here. Assertion confirm. Guess we could run the instructions from DDR. Just did too many changes. I don't know what's up. This doesn't work. We have to assume it's the OCM instruction memory causing issues, which would be weird. It's running here. So we got like what, a 0.9 bolic exertion again? Okay. So we are going to redo everything step. Here. Be happy. You just magically stop working. I'm gonna power cycle the board and we'll try again. Okay. Let's see if it works. Weird. Okay, so time to power cycle the board. Turn the flags off. Linker script change. Could there be something with the R5? Could be. we're going to create a whole fresh application project. That's A53 by itself with the dry stone, because I clearly changed something that broke it. I don't know why. The weird issue. I blame Vitis. No, I don't blame the board. I blame Vitis. Okay. So build. And we're just going to right click, launch on hardware. I don't want to do debug run as. I still want to show you guys the DDR test after this. Oh, this one might be using the first stage bootloader. Are you not happy? Is it because you use the first stage bootloader? Yeah. Let's see if we can kill you. Okay. We're gonna do a good old power cycle. Oh, these lights right here are for 5, 9, and 15 volt. And all three have to be good before you can hit the button and turn it on. So, let's go run configurations. Test me. Target setup. Yeah, we'll try that. Test me. Okay, we're programming the FPGA. We're loading the first stage bootloader. We're running the program. And it immediately goes to the wrong one all the time. Okay, are you going to assert and break? So we're just going to slowly. Okay, cool. 0.7 is garbage. So what we're going to do, the easiest thing, is going to be O3. O3 should work just fine. We're going to rebuild, rerun. You're going to work. Okay, now we go back to A53. Ooh, good number. Okay, the microblaze was a 2 of all the flags. So let's go ahead and add all our flags to. We're going to add, see how much this helps. Okay, so got 3.05. Generate build settings, stations, apply and close, build, run. Okay, yes. Add reset. Okay. Oop. Didn't help. Okay. Linker script. What better latency can we achieve if we stick it all in the OCM memory? Generate. Did we build? Okay, and now we're gonna run. Oop. Okay. Looks like the OCM broke it. What we're gonna do is we're gonna generate linker script, go back to everything being DDR? Is it just me playing with it? There's some, okay. Let's just do that. We're gonna power cycle the board. And I want to see if the error still exists. It might just be an issue in regenerating the linker script, which I wouldn't be surprised. Linker script may be garbage. Let's just go see what the linker script did. Build. And that all looks good. So if we go to debug, double click the elf. Let's look at the contents. What's supposed to, the location for is just the beginning. Yeah. Okay, sure. Let us try to run it. So if this still has an issue, I'm going to blame the linker script generation. Us regenerating the linker script screwed it up. Yeah, it must be a linker script issue. Our linker script is garbage. Okay, let's open a working linker script and see what it looks like. A53 source linker script. Open with a text editor, and we're gonna pop it. Detach. Detach. Right, these should be different. I need beyond compare. Okay. I think these are different. Okay, cool. Let us get these two in an editor and look at them. Okay, so we're going to go to this. Here, view, test SDK. Okay, we're going to say, so this is the working linker script. Did that bad. And then let's go find the not working linker script. Test SDK. Me source. Edit with Notepad++. Move to other view. Move document to other view. Plugins, compare. That's the only difference, the heap size. So it defaulted to a large heap size. Okay, so I guess we broke it with the heap size. Let's go and try that. Stupid heap size. Okay, so here we're going to do a 2-0 and a 2-0. Enter. Save the linker script. Build test me. And we're going to run. That would make sense. I thought the whole linker script was always going to 1 kilobyte, but it looks like it's going to 8 kilobyte for the default stack and heap. I wish it told us that the heap and stack were too small. Those are hard issues to debug, but you should always have a large stack and heap. Okay, that's good. We're gonna regenerate linker script. We're gonna say 8 here. Matched what's supposed to be. OCM. Okay. So we got a 3. Let's see if we can do better than a 3. Hopefully the OCM, it's all local memory. It should run faster. Nah, okay. I'm surprised it's not a lot better. The R5s did pretty good. I guess the dry stone's a pretty pathetic benchmark. We should probably look at a more sophisticated core mark. We don't have core mark. Okay, so let's go do a DDR test. We can look at how we would test, do some DDR test. Okay, cool. Yeah, we're going no back. We want the A53. Did I move you? I'm sorry. Okay, we're gonna go do the DRAM test and finish. Build and run. Pretty easy. Build. And then we're gonna right click it. Launch on hardware. Yeah, it's okay. And then after DDR test, we'll call it a night. So we're gonna go here. We're gonna detach. Hit a full screen, not that screen, this screen. Okay, so this is our DDR test. We're gonna go look at do some analysis and just show you the different ways you can check the PSDDR. So you can do a quick validation of a small address space, and we have no errors. Good. Yeah, no problems. Okay. So if we wanted to test the whole memory range, we would go for the 1 gigabyte, which is 6. It's going to take a bit. We'll do that in a second. We're going to do R, which is the read I analysis. So right now it's changing the offset of like the I. We're doing reads. We're doing the O delay. We're changing the O delay, and we're trying to see when we see errors. These are counting the errors. So you can see right now we have a really wide margin. We can overclock these DDR. I know we can. We need to figure out how. Because we had a good window right there. Look, that's like 70 clicks. We can go faster. Okay. Yeah, we got a lot of room. If we go look at the rights, we could have a similar thing. Sorry. Yeah, I'm gonna have to play around with following how that DDR5 works and how we can go faster. This would be modifying the first stage bootloader because we'll probably want to do it on Linux. Okay, so let's look at the 2D window for the read I analysis, and hopefully it doesn't take too long. Wish I understood a little bit more what this printout is. I assume this is like before we saw the different, it's like the number ranges before we hit a burr. Maybe if we turn verbose mode on. Well, I'll probably do an outro relatively soon. But this is the board. The processors work. We can run the benchmarks on the soft processor, the microblades. We can run it on the A53s and the R5s. We can also perform analysis on a DDR. See, it's in pretty good condition. Probably could overclock it, if Vivado lets you. So what's next? We did do some power testing on the FPGA. I did earlier yesterday. I did some power testing on the FPGA. I would love to do a dynamic clock, maybe with a microblaze system set up where we can just slowly, or do it with the processor. I should probably learn how the dynamic clock works in here. So I would love to use a PLL, and yeah, we'll do a microblaze and just slowly crank up the clock and watch the power consumption and watch the sys monitor. That would be, I think, interesting educational, but when we get around to that, that might be a few weeks. I might just, maybe I'll try to do a short or a video on it separately. We'll see how that goes. I don't know what else we're gonna learn from these DDR tests. They're useful, but they're just numbers at the moment. So let's see. Monday, I want to look at the ePhoenix tools. So I'll do some tutorials this weekend and post some information on the Discord. Feel free to join, it's in the description, and we'll see those tools in action. Friday next week will probably be a Fusion IO card, and the Monday after that will probably be the Flux AI PCB developer. Okay, I think that's probably a good plan. See you all Monday on the stream. I think Monday-Friday schedule is working pretty well. And I want to do shorts and other videos during the week, but we'll see when the schedule fits that. Well, thank you for watching. We could leave the numbers up, but I think we're just going to end it.